Here's how I'll approach this. I'll walk through requirements and assumptions, scale estimates, API and data model, high-level architecture, deep dive, bottlenecks and scaling, trade-offs and summary, complete architecture. First, let's discuss functional requirements. The system must provide continuous service availability, allowing users to access and interact with applications without interruption. It should support automatic scaling of workloads based on demand, ensuring performance meets user needs even during peak usage. Additionally, it must include robust logging and monitoring capabilities to track system health and diagnose potential issues in real time. Lastly, the system should facilitate seamless deployment and rollback of applications to ensure quick recovery from failures. Next, we have non-functional requirements. The system must achieve 99.99% availability, requiring effective fault tolerance and recovery strategies. Latency should be minimal, ideally under 200 milliseconds for user-facing applications, as delays can negatively affect user experience. Consistency is crucial, ensuring that all nodes reflect the same data state, which can be achieved through consensus protocols and distributed storage systems. Now for explicit assumptions. It is assumed that Kubernetes can manage containerized applications to ensure resilience and fault tolerance. The design presumes AWS infrastructure will be reliably available, and that necessary regions support the services we plan to use. Out of scope are non-cloud environments where IaaS capabilities may not apply, and third-party dependencies that could introduce single points of failure. Thank you for the opportunity to present these requirements and assumptions. Let's dive into the scale estimates for our system designed to achieve 99.99% availability through a regional failure using Kubernetes on AWS. First, let's establish that we are targeting a daily active user count of around 5 million. Given that a typical user might perform 10 actions per day, this results in 50 million total actions daily. For read versus write queries per second, assuming a ratio of 80 to 20 in favor of reads, we can estimate an average read QPS of approximately 3,000 and write QPS of around 750. At peak times, we should conservatively double those numbers to 6,000 for reads and 1,500 for writes. Moving on to storage, if each user generates about 1 megabyte of data annually, that scales to 5 petabytes per year just for user data. Concerning bandwidth, if we consider that each user action averages about 200 kilobytes, that results in a throughput of around 12 terabytes daily. Again, during peak usage, we should consider a surge factor of 3, leading close to 36 terabytes for our busiest periods. Finally, continuous replication and load balancing across multiple regions will help ensure that we maintain the required availability, which is balanced against operational costs. This architecture gives us a robust plan for handling failures while meeting user demands. Today, I will outline the key public API endpoints and the core data model for our system, designed to maintain 99.99% availability during regional failures using Kubernetes on AWS. Our API consists of several key endpoints. The first is Get API v1 Resources, which retrieves a list of resources. Each resource includes fields such as ID, name, type, and status, ensuring clients can filter based on type and status. The second is Post API v1 Resources, allowing clients to create new resources with a payload that requires name and type. Thirdly, Get API v1 Resources/ID lets clients fetch details for a specific resource. A crucial endpoint is Put API v1 Resources/ID, which updates existing resources, while Delete API v1 Resources/ID enables resource removal. Now moving on to our core data model, we focus on the resource entity. It contains key fields like ID, name, type, status, and region. The ID serves as the primary key, supported by indexes on type and status for efficient querying. To maintain high availability, we implement sharding by region, which distributes data across multiple Kubernetes pods in different availability zones. This design ensures resilience against zonal failures. Furthermore, we implement replication across regions, allowing for seamless failover when required, guaranteeing both data integrity and quick access. In this architecture, we start with the clients who initiate requests to our services. These could be web or mobile applications that generate traffic. To manage this incoming traffic effectively, we employ a load balancer. The load balancer distributes the requests across multiple instances of our backend services running in Kubernetes. This ensures that no single instance becomes overwhelmed, thus enhancing performance and availability. Once the load balancer forwards the request, it routes to one of our Kubernetes services. Each service is responsible for specific functionality, and they are all designed to scale horizontally and manage state independently. This architecture allows us to update services independently, which is crucial for maintaining high availability. For state management, we use caches like Redis, which store frequently accessed data to reduce latency and improve response times. This results in quicker request handling. Requests that need persistent storage interact with our data stores, which could be Amazon RDS or DynamoDB, both configured for high availability across multiple availability zones. We also implement message queues like Amazon SQS for handling asynchronous tasks. This decouples our services and enhances reliability. If a service is down, requests can be queued until the service recovers. This layered architecture allows for failover and redundancy, ensuring we maintain 99.99% availability even during regional failures. To achieve 99.99% availability in our system during a regional failure, we begin with a microservices architecture deployed on Kubernetes across multiple AWS availability zones. Our core data structure utilizes a distributed key-value store like Amazon DynamoDB, leveraging its eventual consistency model to ensure high availability while managing concurrency through optimistic locking. This allows multiple services to read and write data simultaneously without blocking, enhancing performance while minimizing downtime. Data flow starts with client requests hitting an API gateway, which routes them to respective microservices based on service discovery, integrated within Kubernetes. Each service has its own read replicas, distributed across multiple regions, which aids in minimizing latency and enhancing data read throughput. To ensure atomicity during write operations, we employ transactions within DynamoDB, enabling coordinated writes across multiple key-value pairs. For scenarios requiring immediate consistency, we can combine strong read-through caching strategies via Amazon ElastiCache, which helps alleviate read-heavy workloads. However, we must be cautious with trade-offs between consistency and availability. Using an eventual consistency model means we need robust mechanisms for handling stale reads and ensuring idempotency to avoid data corruption. Thus, we utilize versioning of records and client-side timestamps to track changes. By designing with these considerations, we maintain robustness against failures while ensuring system performance and reliability. First, a significant bottleneck in our system can occur at the database layer. To scale past this, we can implement database sharding and read replicas. This allows us to distribute the load effectively and handle increased read and write operations concurrently. Next, we consider the application server. A potential bottleneck here is resource exhaustion under high load. We can use horizontal pod scaling in Kubernetes to add more replicas of our application instances based on demand metrics like CPU and memory usage. Network latency can also be a bottleneck, particularly in regional failures. To mitigate this, we can deploy a multi-region setup with cross-region load balancing, ensuring users are routed to the closest available resources. For data storage, using an object storage solution like Amazon S3 ensures durability and unlimited scaling, removing the risk of hitting storage limits. Finally, regarding failure modes, we must think about node failures. Leveraging Kubernetes self-healing capabilities allows for automatic rescheduling of pods on healthy nodes. We should also prepare for service dependencies, where a key service might fail. Implementing circuit breakers and retries in our service mesh architecture can help manage these failures graciously, minimizing impact to user experience. In summary, our strategies encompass sharding, horizontal scaling, multi-region deployments, self-healing orchestration, and resilient service architecture to achieve 99.99% availability. In designing a system for 99.99% availability through regional failure on Kubernetes and AWS, we prioritized resilience and scalability. We decided to deploy across multiple availability zones. This choice ensures that if one zone fails, the application remains operational in others, though it increases complexity and costs. For the database layer, we opted for Amazon Aurora with multi-region replication. This offers high availability and performance, but requires careful synchronization management, which adds overhead. We also chose to implement a load balancer with health checks to route traffic effectively, enhancing the system's responsiveness and reliability, but slightly increasing latency during failover conditions. Regarding container orchestration, we selected Kubernetes due to its robust ecosystem for managing microservices, despite its steep learning curve and operational overhead. We opted for horizontal pod autoscaling to handle traffic spikes efficiently, though it could lead to resource wastage if not properly configured. Monitoring and alerting are implemented using Prometheus and Grafana, which provide rich insights into system health, but introduce additional operational management tasks. In summary, our design balances availability, performance, and cost efficiency by leveraging AWS's multi-region capabilities and Kubernetes orchestration to create a resilient cloud-native architecture that ensures continuous service delivery even in the event of regional outages. In this architecture diagram designed for 99.99% availability during a regional failure, we start with the clients, which include web applications, mobile apps, and third-party API consumers. They initiate requests that are routed through Route 53 for DNS management, directing traffic to CloudFront, our content delivery network, for caching and acceleration. The next layer consists of AWS WAF for security against web attacks and AWS Shield for DDoS protection, ensuring our application remains resilient under load. The Application Load Balancer (ALB) manages global traffic distribution, helping in load balancing across regions. Requests are then processed by our API gateway, which serves as a central point for routing, authentication via AWS Cognito, and has built-in rate limiting using AWS API Gateway usage plans. Each region has its own ALB for local load distribution. Our core services are hosted within a Kubernetes cluster on Amazon EKS, where multiple microservices operate. These include the user service for registration, the auth service for authentication, the order service for managing customer orders, the product service for inventory, the payment service for transactions, and the notification service for alerting users. A background worker service handles asynchronous processes. For caching, we utilize Amazon ElastiCache with Redis to store user sessions and product details, enhancing performance significantly. Important data resides within Amazon RDS using Aurora for relational needs, featuring read replicas across availability zones for read scalability and reliability, and sharding for efficient data management. Although Amazon DynamoDB is used for document storage of our product catalog, supplemented by OpenSearch for search capabilities. Asynchronous communication is managed using Amazon SQS for event handling and Amazon SNS for notifications. For storage, Amazon S3 holds user-uploaded media, with versioning enabled. Cross-cutting concerns like observability are addressed through Amazon CloudWatch, while AWS Secrets Manager secures sensitive credentials. Our CI/CD pipeline is managed by AWS Code Pipeline, and to ensure disaster recovery, a multi-region deployment strategy is in place with duplicate EKS clusters in a secondary region. Throughout this architecture, data flows seamlessly from clients through the layers to the appropriate microservices, ensuring both robustness and scalability with 99.99% availability.